Okay. So, hi everyone. So, good afternoon. Good afternoon, all. Okay. So, today, we are dealing with the subject electromagnetics. And in electromagnetics, we have started magnetostatics. Okay. So, let me know whether audio and video everything clear here. Let me know, is audio and video everything clear? Tell me here. Okay. So, in magnetostatics, we have covered a Lorentz force equation, right? So, then we have started Biot and Savart's law. We have seen the applications of Lorentz force equation, and we have seen the applications of Biot and Savart's law, right? Okay. So, next we have started with Ampere's law. Next we have started with Ampere's law, right? Okay. So, what I have told here in Ampere's law. So, in Ampere's law we have seen both integral form and differential form of Ampere's law. So, what we have seen here, so that is the circulation of B field, around any closed loop is equivalent to what? Is equivalent to mu times of what? Mu times of current enclosed by that closed loop, or we can say I penetrating, right? Okay. So, that is the current penetrating through the surface which is enclosed by the closed loop. Understood? Okay. So, this is what we have studied, and we have represented the same expression here. So, the circulation of B field around any closed loop is equal to what? Is equal to mu times of we have represented this current in terms of what? In terms of current density. So, how we have represented here? We can represent in terms of current density as a double integral Z bar dot what? Z bar dot dA bar, right? Okay. So, this we call as a integral form of what? Integral form of Ampere's law. So, this we called as a integral form of Ampere's law, right? Okay. Next we have applied here, so to this LHS side, we have applied what here? We have applied Stokes theorem. So, we have applied Stokes theorem to this LHS side. So, then how we have written here this one? So, this one we have written as a double integral del cross B bar dot what? Dot dA bar is equal to what? Is equal to mu times of double integral Z bar dot what? Z bar dot dA bar. Now, here the surface integral on both sides will get what? Will get cancelled. So, therefore, we can write del cross B bar is equal to what? Del cross B bar is equal to mu into what? Mu into Z bar, or we can write we know that B bar is equal to what? B bar is equal to mu into H bar. So, just substitute in place of B bar, just substitute mu into H bar here. So, what you are going to get? Mu into curl of what? Curl of H bar is equal to what? Is equal to mu into what? Mu into Z bar. Now, here mu will get cancelled. So, therefore, we are going to get what? We are going to get del cross H bar is equal to what? Is equal to Z bar. So, this we call as what here? This one or this one. So, this we call them as a point form or differential form, right? So, point form or a differential form of Ampere's law. Right? Okay. Okay. So, these things we have seen. Right. So, that is integral form of Ampere's law we have seen, and also we have seen how to represent the point form or differential form of Ampere's law. So, these things we have seen here, So, next, okay. So, next in the previous session we try to determine the B field, we try to determine the B field in all the regions. So we have considered a cylindrical wire, we have considered a cylindrical wire of radius rho, yes or no? So we have considered a cylindrical wire, we have considered a cylindrical wire of radius. So let us say this is the axis of the wire, right? So this is the radius, let us say the radius of the cylindrical wire is rho. Okay, so if the current flowing through this cylindrical wire is I, right? So where I is uniform current, I is uniform current, right? So in this case we try to determine the B field in all the regions here. So that means we try to determine the B field for R greater than rho, and we try to determine the B field for R less than what? For R less than rho, and we try to determine the B field for R equal to what? For R equal to rho. Right. Okay. So what are the expressions we got here? What are the expressions we got? So the B field outside the cylindrical wire, that is for R greater than rho. For R greater than rho, what is the B field we got? Tell me. What is the B field here? We got for R greater than rho. So that is outside the, so that is somewhere here. Let us consider at some point this is R greater than what? R greater than rho. So at that point we try to determine the B field. So what is the B field we got? What we have done? We have enclosed this current carrying wire with what? With a circular loop, with a circular loop. Then we have applied what? Then we have applied Ampere's law. So what Ampere's law says? So that is nothing but the circulation of B field, the circulation of B field around this closed loop is equal to what? Is equal to mu times of current enclosed by this closed loop. So what is the current enclosed by this closed loop? That is nothing but I. So we have already done all these derivations here, right? Okay, okay. So here B is in A phi cap direction, this differential length is also in A phi cap direction. So finally what is the expression we got here on LHS side? We got B into what? B into circumference of this circle. So that is B into 2 pi R. 2 pi R is equal to what? Is equal to mu times of I. Therefore B field is equal to what? B field is equal to mu I by what? Mu I by 2 pi R A phi cap. So this is the expression for B field we got. This is the expression for B field we got for R greater than what? For R greater than rho. For R greater than rho. Okay. So that is outside the current carrying wire. Next, similarly for R less than rho here. For R less than rho. So that means inside the cylindrical wire, we have determined what? We have determined the B field. So what is the B field expression we got here? So here what we have done? So we have considered some point inside the cylindrical wire. Let us say this point. So this is R less than what? R less than rho. Okay. So at this point, if you want to determine the B field, what we have done here? We have formed what? We have formed a circular loop. And then we have applied what? We have applied simply Ampere's law. Yes or no? So what we got here? What we got? I am writing directly here. We got a B into 2 pi R is equal to what? Is equal to, we got a mu into, what is the current enclosed by this loop here? So the current enclosed by this loop is nothing but the current that is penetrating through this surface. So what we got? So mu into I by pi rho square into pi R square, right? Okay. Okay, so here pi will get cancelled. So we got here R will get cancelled. We got mu into IR divided by what? Divided by 2 pi rho square A phi cap. So this is the expression we got. This is the expression we got for B field inside what? Inside the cylindrical wire. Inside the cylindrical wire, right? Okay. Okay. So this is the expression we got for R less than what? For R less than rho. For R less than rho. So next for R equal to rho here. For R equal to rho, what is the expression we got here? What is the expression for B field we got? For R equal to rho. For R equal to rho, what is the expression we got? So either in this expression or in this expression, just substitute in place of R. In place of R, just substitute rho here. So then what you are going to get? Tell me. So B is equal to what? B is equal to mu into I divided by what? Divided by 2 pi rho. So this is the expression we got for what? For the B field on the surface of what? On the surface of the cylindrical wire. Okay, so this is the expression for B field we got for the, if the point is lying outside the cylindrical wire, and this is the B field for the if the point is lying inside the cylindrical wire, and this is the B field on the surface of what? On the surface of cylindrical wire. Okay, so we got all these three expressions here. We got all these three expressions, that is outside the wire, inside the wire, and on the surface of the wire. So and also we have drawn the graph here. We have drawn the graph. Yes or no? Okay, so this is R and this is B. So we have drawn the graph B versus what? B versus R. So this is R equal to rho, this is R greater than rho, and this is R less than rho. So for R equal to rho, that is on the surface, what is the B field we got? Mu I by what? Mu I by 2 pi rho. And for R less than rho here, for R less than rho, so this is the expression. This is the expression for R less than rho. So if you observe this expression here, mu is constant, I is constant, 2 pi is constant, and rho is also constant. So B is proportional to what? B is proportional to R. So that means inside the wire, as R increases, B field is also going to what? Is also going to increase. Right? So B is proportional to R. Why here? Inside the wire here, inside the cylindrical wire, as R increases, what will happen here? The current enclosed by the loop is also going to increase, and hence B field is proportional to what? B field is proportional to R. So inside the wire, and it will become what? It will become maximum on the surface of the wire. So once you come out of the wire here, once you move away from the surface of the wire, then what will happen? The current enclosed will remain same, but the distance from the current carrying wire is going to increase. The distance from the current carrying wire is going to increase, but the current enclosed by the by the loop will remain what? Will remain same. Understood? So as you move outside the loop, as you move outside the current carrying wire, then what will happen? The radius of the current carrying wire, the radius of the loop is going to increase, but the current enclosed by the loop will remain same, and hence B field is going to decay as what? B field is going to decay as 1 by R. Understood? So outside the cylindrical wire, B field is equal to what? Mu I by 2 pi R. Here mu is constant, I is constant, 2 pi is also constant. So B is inversely proportional to what? B is inversely proportional to R. Yes or no? So for R greater than rho here, what will happen here? So the B field is going to decrease. So B field is going to decrease as what? As 1 by R. As 1 by R. So that is outside the cylindrical wire. Understood? So all these things we have seen here. So now we try to represent the expressions in terms of current density also. In terms of current density. Here we have represented the expressions in terms of what? In terms of what? In terms of I, right? We have represented the expressions in terms of what? In terms of I, right? Okay, so now we try to represent the expressions for B field in terms of what? In terms of current density. Right? Okay, so what is current density here? So I is equal to what? I by A. Wait. Okay, so here I by A is equal to what? Is equal to current density Z. So therefore I is equal to what? I is equal to Z into A. So that is Z into what? So what is this area of this cross section here? What is the area of this cross section? Tell me. So the area of this cross section is nothing but what? Pi into rho square. So this area is nothing but what? Pi into rho square. So in place of I here, in place of I, just substitute Z into what? Z into pi rho square. Okay. So then you are going to get the expressions in terms of what? In terms of current density. So see here. So for R greater than rho here, for R greater than rho, what is the expression you are going to get? Tell me. So B bar is equal to what? Mu into, so what is I here? What I have told, I you can replace with what? Replace with current density. So that is I is equal to what? J into pi rho square. So substitute I is equal to J into pi rho square in these expressions here. So mu into I is nothing but what? J into what? J into pi rho square. J into pi rho square divided by what? Divided by 2 pi r a phi cap. Right? Okay. Now here pi will get cancelled. So therefore B field is equal to mu into rho square into J divided by 2r a phi cap. So this is for what? This is for r greater than rho. This is for r greater than rho. Okay. Okay. So next. Okay. Next for r less than rho here, for r less than rho, what you are going to get, tell me? So B field is equal to what? Is equal to, so for r less than rho, this is the expression. So in place of I, substitute J into what? J into pi rho square. So we are trying to get the expressions in terms of what? In terms of current density, right? Okay. So in place of I, substitute J into what? J into pi rho square. So what you are going to get? Mu into J into pi rho square into r, right? So mu into J into pi rho square into r divided by what? Divided by 2 pi rho square, divided by 2 pi rho square. So this is for r less than rho. So here pi will get cancelled, rho square will get cancelled, right? Okay. So therefore B field is equal to what? Is equal to mu into J r divided by what? Divided by 2 a phi cap. So this is the expression for B field inside the current carrying wire in terms of what? In terms of J bar. Understood? Okay. Okay. Yeah. Next for r equal to rho here, for r equal to rho. So for r equal to rho, so what you are going to get? So just substitute in place of r, just substitute rho here. So what you are going to get? So you are going to get a B field, B bar is equal to what? Mu into J rho divided by what? Divided by 2 a phi cap. So these are the expressions for B field. These are the expressions for B field in all the regions. So if you are having a current carrying wire, of radius rho, then these are the expressions for B field in all the regions here, that is outside the wire, inside the wire, and on the surface of the wire, Understood? So we got the expressions in terms of what? In terms of current, in terms of I, right? And also in terms of what? In terms of J, that is in terms of current density, right? Okay. 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 But here today I am not seeing any viewers. What happened here today? I am not seeing any viewers here. Is there anyone online? Tell me here, is there anyone online? What happened here today? So if anybody is there in online, please give some comment in chat box here. Give some comment in chat box. I am not seeing any viewers at all. Right. Okay. Is there anyone? Okay. All right. Okay. We try to solve this problem here. So this question is given in gate. So this question is given in gate, right? Okay. See here, what is the question they are asking here is two identical copper wires W1 and W2 placed in parallel as shown in figure. Placed in parallel as shown in figure. Two identical copper wires W1 and W2 are placed in parallel as shown in figure. So carries current I and 2I, carries current I and 2I respectively. So that means W1 is carrying the current I and W2 is carrying the current 2I. Okay, so respectively means W1 is carrying current I and W2 is carrying current 2I in opposite directions. In opposite directions, right? Okay. कुमार सर प्लीज़ डिस्करेज मत होए, आपका कंटेंट एक नंबर है. Okay. It's not like discouraging here, but whenever we are giving some good content, there must be some receivers also, na? Then only we will get some encouragement, right? Okay, so students are the strength for faculty here, right? So that's it, nothing else, right? Okay. Two identical copper wires W1 and W2 placed in parallel as shown in figure carries current I and 2I respectively in opposite directions. If the two wires separated by a distance of 4r, if the two wires are separated by a distance of 4r, then the magnitude of B field between the wires at a distance r from W1 is. Okay, so that means here they have given two current carrying wires here. They have given two current carrying wires, right? Okay, so this wire 1 they have named it as W1 and this is wire 2 that is named as W2, and they are saying that W1 is carrying a current I and W2 is carrying a current 2I, but they are carrying the currents in opposite directions. So that means if you consider for W1, if you consider the current from left to right, then you have to consider the current for W2 from right to what? From right to left. Okay, so that's your wish here, that's your wish. So if you consider I in this direction, then consider 2I in this direction, or if you want, if you consider I in this direction, then consider 2I in this direction, right? Okay, okay, yeah. So both are going to be in opposite directions. So that's what they have given. Now they are asking to determine the B field. They are asking to determine the B field between the wires at a distance r from W1. So that means this is W1 at a distance r from W1. They are asking to determine the B field. So that means at some location here, at this point. So at this point they are asking to determine the B field. Understood? Okay, so we know the expression for a B field due to a current carrying wire. Yes or no? We know the expressions for B field due to a current carrying wire. Understood? Okay, see the distance from here to here is r, so that means the distance from W2 to this point is how much here? Is nothing but what? Is nothing but 3r. Why? Because the total distance from here to here, from here to here, the total distance is nothing but what? Is nothing but 4r. Is nothing but 4r. Okay, so it's nothing but 4R. Now okay, so now we know that B field, due to a current carrying wire of infinite length, is what here? Is what? B is equal to what? B is equal to mu into what? Mu naught into I divided by what? Divided by 2 pi R, where R is the normal distance, from the wire. Yes or no? So this is the expression for B field here. See here, they are asking only magnitude here. They are asking only magnitude of B field they are asking, right? So just write down the magnitude. So magnitude of B field due to a current carrying wire of infinite length is how much here? Mu naught I by what? Mu naught I by 2 pi R. Where R is the, or you can write instead of R, you can write rho here. Okay, so where rho is what? Where rho is the normal distance. From what? Normal distance from wire. Normal distance from current carrying wire. So this is the general expression for B field due to what? Due to a current carrying wire. Understood? Now consider this W1 here. So due to this W1, what is the B field at this location here? So at this location, B field I am representing as B1 here due to W1. So B1 is equal to what? B1 is equal to mu naught into what? Mu naught into I. The current is nothing but I divided by what? Divided by 2 pi. What is the normal distance from the wire to this point here? Is nothing but R. So just substitute here R. So this is the expression for B field at this location, right? Okay, next, due to this current carrying wire here, 2I, what is the B field at this location here? Due to this current carrying wire W2, what is the B field at this location? Tell me. So B2 is equal to what? B2 is equal to, so mu naught into what is the current? What is the current carried by W2? Is nothing but what? Is nothing but 2I. Divided by what? Divided by 2 pi into what? Normal distance from W2 to this point here. So what is the normal distance from W2 to this point here? Is nothing but 3R. So this is nothing but 3R. Understood? So we got the expressions for B1 and B2 here due to this current carrying wire W1 and due to this current carrying wire W2. Understood? But here we have to add these two fields, or we have to subtract these two fields in order to get the total B field here. In order to get the total B field at this location, B total at this location, we have to add this B1 and B2, or we have to subtract B1 minus B2 or B2 minus B1. So what you have to do? Okay, so for that, what we have to determine here? We have to determine the direction of B field also. So if B1 and B2 both are pointing in the same direction, then they are going to get added up, right? Okay, so if they are pointing in opposite directions, then it is going to get subtracted. Understood? Okay, now see here, from right hand rule, see here, the current is flowing from left to right here. Understood? So that means the B field is going to circulate around this wire. So how it is going to circulate here? Above this current carrying wire W1, the B field will come out of the board, and below this current carrying wire W1, B field will go into the board. So that means here B1 is pointing what? Is pointing into the board here. So for example, let us consider this as what? This as x-axis and this as y-axis, and let us consider this as z-axis. Understood? So into the board means it is pointing in which direction? Negative z direction. So B1 bar is going to point in negative z direction. So generally we will represent with what? If it is pointing into the board means we will represent it with what? So B1. Okay, so it is pointing into the board, right? Okay, now what is B2 here? What is the direction of B2? See here, 2I current is flowing in this direction, that is from right to left. It is flowing in this direction. So if it is flowing in this direction, above this current carrying wire, the B field will point into the board, and below this current carrying wire, B field will point out of the board. Yes or no? See here, 2I is flowing in this direction. So above this wire here, above this wire, B field will point into the board. So that means B2 will also point into the board here. B2 will also point into the board. So that means B2 is also pointing in which direction? Negative Z direction. Understood? Okay. Okay here. Now if you observe B total here, what you are having here, B1 bar is pointing into the board, B2 bar is also pointing into the board. So that means both are pointing in the same direction. That means you have to add these two fields here. You have to add these two fields in order to get what? In order to get the total B field or net B field at some point here, which is at a distance R from W1. Understood? Okay. So B total is equal to what? Is equal to B1 plus what? B1 plus B2. Both are pointing in the same direction. So that's why I am adding up those two. Right? Okay. Okay. Yeah. So if you add these two, what you are going to get? Tell me. So therefore B total is equal to what? Is equal to B1 is mu naught I by 2 pi R. B2 is what? Mu naught into 2I by 2 pi into 3R. So from these two, what I can take common here? I can take mu naught I by 2 pi R common. Right? Okay. So I can take mu naught I by 2 pi R common. Now what is left out here? What is left out? Here you are having 1 plus what? Plus here what is left out? 2I divided by what? 3. Sorry, 2 divided by 3. So 2 divided by 3. I also we have taken common now. So here you are going to get 2 by 3. Right? Okay. Okay. Yeah. So therefore B total here. Therefore the total B field is equal to what? Is equal to mu naught I by 2 pi R into what? Into, so 3 plus 2, that is 5 by 3. You are going to get 5 by 3 here. So therefore total B field here. Therefore total B field at some point here, which is at a normal distance R from W1, is how much here? 5 mu naught I is equal to what? Is equal to, you are going to get 5 into mu naught I divided by what? Divided by 6 pi R. So this is the expression for B field. If suppose they would have asked a direction here, then what is the direction of B field? Due to this one, it is pointing negative Z direction. B2 is also pointing in negative Z direction. So the total B field or the net B field will also point in which direction? Negative Z direction. Understood? Okay. So in this manner, you have to determine what? You have to determine the total B field here due to these two current carrying wires. So this question is given in gate here. This question is given in gate, which is very, very simple here. Right? Okay. So which is the answer here for this question? 5 into mu naught I by 6 pi R. 5 into mu naught I by 6 pi R. So that is option B. Option B is correct. Option B is correct for this question. Right? Okay. 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 So next question here. Next question. See here. So this question is also given in gate here. This question is also given in gate. Right? See here. What is the question they have asked? See here. So an infinitely long uniform solid wire of radius A. An infinitely long uniform solid wire of radius A carries a uniform DC current density Z bar. An infinitely long uniform solid wire of radius A carries a uniform DC current density, that is Z bar. Okay. So the first question they have asked here is, see, this is statement linked answer questions here. Understood? Okay. So they will give two questions. So this is first question, and whatever the answer we are going to get in first question, that will be linked to what? If you get the answer for first question, then only you can get the answer for second question also. Understood? So that's what we call as linked type questions here. linked type questions, linked answer questions. Understood? So nowadays this type of questions are not there in GATE. Okay, so previously it was asked here, previously it was asked, right? Okay, so an infinitely long uniform solid wire of radius A carries a uniform DC current density Z bar. The magnetic field at a distance R, the magnetic field at a distance R from the center of the wire is proportional to. The magnetic field at a distance R from the center of the wire is proportional to. See, what they are asking here is you are having a uniform, you are having a current carrying wire. We have already done this one here. Okay. I will okay. See here. So we have already determined this one. So if you are having a current carrying wire, right? Okay. Of radius. So here they have given the radius of this wire. The radius of this wire they have given as what? They have given as A. They have given as A. Understood? Okay. So it is carrying a uniform DC current density Z bar. So let us say the current density is Z bar here. The current density is Z bar. So Z bar is uniform. Z bar they have given as what here? It is uniform. So that means it is uniform current density. So that means the current is distributed uniformly over this cross section here. That's what they mean. Okay. So in the last class itself, I have explained how to determine the B field. If you are having what? If you are having a cylindrical wire of radius rho, there I have told the radius rho, and it is carrying a uniform current I. It is carrying a uniform current I. Understood? Okay. So if the current I is uniform, means the current density is also what? Current density is also uniform. Understood? Okay. Okay. Yeah. Now here, see here, an infinitely long uniform solid wire of radius A and carrying a uniform current density of Z bar. Understood? So for this one, we know for R greater than A here, for R greater than A, what is the expression for B field? Just now we have determined B field is equal to what? B field is equal to mu I by what? Mu I by 2 pi R. Mu I by 2 pi R A phi cap. So this is the expression we got for what? For R greater than A, that is outside the cylindrical wire. Understood? Next, for inside the cylindrical wire here, for inside the cylindrical wire, that is for R less than A, for R less than A, what is the expression we got? B bar is equal to mu I into R divided by what? Divided by 2 pi rho square. Yes or no? So this is what we got, right? So I think this is the expression we got, right? For R less than A, mu I R by 2 pi rho square. Yes. Mu I R by here happened here. Wait. Question was gone here. Oh my God. What happened here? Question was also gone. Okay. 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 So I will take up the question here. I will take up that question. So okay. So I don't know how it is deleted. So somehow it get deleted, right? Okay. Okay. So with this here, with this I am winding up the session for today. So I will discuss that problem tomorrow here. In tomorrow's class, I will discuss that problem. right? Okay, so that linked answer type question, and also I will discuss some more problems here tomorrow. Okay, so with this I am winding up the session. So tomorrow we'll meet exactly at 4 p.m. here. Tomorrow we'll meet exactly at 4 p.m. right? Okay, so please share the session and try to attend a more number of students here in live. Okay, so if one person or two persons are there, okay, so it is somewhat very difficult for a teacher to teach also, right? If nobody is listening, then what is the purpose of our teaching, right? Okay, so please share the session here, please share the session to more number of students, and if more number of students will be present in live, it's going to be very good here. At least 3 to 4 members must be present now. So that is also not there today. So I don't know what happened today. I don't know that, right? Okay. Okay. Yeah. So tomorrow we are going to meet at the same time, that is 4 p.m. So with this today I am winding up the session here. I am winding up the session. So we'll meet tomorrow exactly at 4 p.m. So until then, take care. Bye bye.